Probably you unshared the screen.
Yes.
Right. Yes. Okay. Great.
We're all set.
Okay. And this is being recorded. Yeah.
Yeah. Okay. So good. Let's get this thing started. Come on. All right. So an official welcome to all of you to this logic mini course, and the purpose of this introductory lecture is really the very informal way of presenting you the material. So, and actually the emphasis on really my part here is to motivate why you're actually sitting to this topics in logic, probability, and computation. Okay, we assumed, and I think this assumption is actually pretty much correct, that you don't have any specific background in this field. So that was actually our challenge, to try and say something interesting to all of you, assuming that you all have really distinct backgrounds and none of you actually knows very much about the topics. So as you can imagine, that's a very simple task. So some motivation, really. The whole table of contents is really motivation. I'll give you a general motivation, and then I'll try and motivate the specific topics that you'll see something about in this course. Okay, and I'll give you some conclusions. So it's mind, brain, and reasoning, and let's just warm up with something I hope is familiar. So all men are mortal. Socrates was mortal, and I think you know how this goes on. Do you? Yeah. Is all men are Socrates, right? So this is actually you probably know this if you know this at all from Love and Death, but it's actually in the Getting Even anthology by the great Woody Allen. So I hope you believe this is really not a valid conclusion. And the point of reasoning is, if there is any point, and this is actually a question that I would like to ask you in the first place, but if there is any reason at all to actually do logic, to do reasoning, that reason is that you would like to say this should not follow, right? If you agree on that, that still doesn't address the question as to why the problem should be tackled by doing logic. So here is an analogy that I found useful in the past, and I hope it's still useful for you today. So I think that reasoning is something which really, well, there are medical doctors in the audience, so you probably know better than myself. Reasoning is a bit like breathing, and breathing is, of course, a necessary condition for our survival. I mean, the very fact we're here means that we can all breathe, okay? And nevertheless, breathing techniques are being taught in a number of situations, in a number of contexts. And indeed, those techniques are necessary to do a number of things, right? There's a very long list, in fact, if you try and look for the details, but here is a very short list. And actually, these activities are grouped by the reasons why you should learn breathing techniques. So the first kind of reason is that by learning breathing techniques, you become aware of things that you otherwise do mostly without you being aware of it. So non-conscious activities. And in fact, that of breathing is mostly non-conscious, right? I don't dare really doing more details here because there are neuroscientists in the audience, but I think what I'm saying is defensible, right? Most of the time you're not aware of the fact you breathe. Sometimes you are. And actually being aware of that is very useful in a number of either ordinary or extraordinary ordinary activities like meditation and anxiety management and very many others. So that's one kind of line of reasoning. Another one is more specific, if you like. Learning breathing techniques just opens up to technical advance. So by this, I mean that you, by learning, by attending breathing techniques classes, you actually learn to do things that you wouldn't be able to do otherwise. Okay, and that is very clear in acting, in certain kinds of free diving, and so on. Okay, so my take is that logic, learning logic, doing some logic has exactly those motivations. So first, being aware of the fact that you reason and that you can sometimes reason in better ways, sometimes in worse ways. So the all men are Socrates example should be reminding you of this. And actually, the perspective that we want to give you with this course, or really chat, if you like, is that learning some logic will be very useful, especially if you do it in combination with some probability, and especially if you do it from a computational point of view, which is exactly what we do here. Okay, so this is the kind of motivation, the overall motivation. But let me just give you some more specific examples. So I really hope that someone, well, not very many of you, but at least someone has seen this before. The first actual motivation really, so I'm in the line here of raising awareness, right? Being aware of the fact that reasoning sometimes is tricky, has a very nice or very important indeed aspect when reasoning is combined with uncertainty, and that's what we call uncertain reasoning. And uncertain reasoning is tricky. So this is a super famous example from Kahneman and Tversky. So it's 1979, so not exactly yesterday. It has been replicated, of course, it's an experimental setting. It has been replicated a very large number of times, and the results of this are very stable. So what's the story here? The story is that you take a group of people, you split it, and you give them this problem. And the problem is as follows. The scenario is kind of uncannily realistic by now. The background story is that there is an unusual epidemic which is expected to kill 600 people. And there have been proposed 2 alternative programs to combat this disease. Okay. Group number 1 gets this alternative between program A and program B. In program A, you just say to people that 200 people will be saved. Okay? Then the alternative is program B, which, if adopted, will save 600 people with probability 1/3 and will kill, so no people will be saved with the remaining 2/3 probability. Which one of the 2 programs would you favor? So that's the actual experimental question. This has been replicated very many times. The there's a very, very strong evidence that when faced with this choice, people prefer program A. Okay. This is already funny enough, if you like. So if you want to read background about this, then look up for the book by Daniel Kahneman, and I'm sure some of you know this already. It's called Thinking Fast and Slow, right? Which actually is a very, very good introduction to the whole field, which I'm aware, I'm sure many of you are aware of already. Please, I didn't say this before, but this is really a chat. So if you have any comments, questions, just jump in as you like. Just feel free to just do that. So thinking fast and slow is it's not really necessary to be learning outcomes of this course, but it's a very good book. So I think if you haven't, yeah. So if you haven't heard of it, is worth absolutely keeping it in your maybe digital bookshelf. So the whole problem is very well described there. So why do I say this is funny enough? Because the two alternatives, program A and program B, actually in probability are exactly equivalent, in the sense that in problem A you say 200 people will be saved, which means, of course, that 400 will be killed. And program B just says the same thing, but in a slightly more complicated way, apparently. You say that you have a third probability of saving 600 people, right? Which means 1/3 probability. So in expectation, you are actually saving 200 people. So 1/3 times 600 is just 200. And 2/3 probability of no people being saved, which is again 400. So 600 minus 200. So it's exactly the same expectation, as you say, in probability, but people massively go for program A. And the reason for this is, of course, this is cognitive psychology. You have to look for stories that account for the deviation from mathematics. And the story is, of course, that people tend to, favor the wording in which they feel they're contributing to saving people. Okay, so that's the general explanation. But what is really even more interesting is the comparison with group B, right? So remember, you split your group. Group B states the problem as follows. If program A is adopted, then 400 people will die, okay? So what happens here, you just negate, right? So let me just get this better. So you negate, really, you're saying the same thing, but now with the connotation of you killing people, right? Everything else stays absolutely the same, just reverse negations. But what happens is that the preference now is flipped. So in group 2, the vast majority of people prefer program B. Okay? So this is a wonderful example of what it means to say that uncertain reasoning is tricky. Okay? The way people apparently cognitively parse the uncertainty in combination with logic is open to rather funny, let me just use this expression, patterns, which are not so funny, because eventually they are predictable. So that's the whole story about thinking fast and slow. You can actually predict how people will deviate from otherwise very simple probabilistic reasoning. So take-home point number 1, the reason why the topics of this course are interesting, I hope, is the key reason is that uncertain reasoning is tricky. It's very easy to actually make slippery inferences when logic is combined with probability. Okay, so of course, knowing a little bit of logic and a little bit of probability and knowing how they actually relate, hopefully will help you not just making this kind of slippery inferences. So that's the first point. Second point, which actually relates to the computational aspect, is really the relevance of uncertain reasoning in current AI. Okay, and I don't mean artificial intelligence just as a theoretical topic, or at least an isolated topic, but something a lot more relevant than that, namely the idea that AI is being massively used in all science, and indeed is coming to be a prominent feature and tool and technique in policymaking as well, and in actually the combination of science and policymaking. So indeed, medicine is really the intersection of science and policymaking from this point of view. And I just picked one of my favorite readings in this. You can click on all the links. I'll give you the PDFs later on. I'll actually upload the PDFs on the team, so you can actually click, but of course you can search for words and find this very quickly. So I don't plan to read this with you. Maybe if you have an interest, we can discuss about this, but this is just to show you that I'm not just saying it might be relevant. It is at the core of current work in medicine, so in particular machine learning. Okay, we're not going to do machine learning, but of course what we're going to do is indeed what machine learning is based on, at least conceptually. Okay, so it's interesting to actually have a look at the abstract. So machine learning is swiftly infiltrating many areas within the healthcare industry, from diagnosis to prognosis to drug development, epidemiology, right, with significant potential to transform the medical landscape. So there's kind of bold statements in here, right? So it's, I guess, given your own PhD, given the background of some of you, I think it's really important that you are aware of actually the conceptual machinery which eventually leads to machine learning. Okay, so again, that's the, let's say, technical motivation. So awareness and techniques, that's my two way of justifying the topics in this course. Okay, so that's general, you know, for everyone. I'd like to give you more precise motivation for you yourselves actually doing this. So you're in this PhD, and we expect that you are, especially, you know, we're concerned with the reasoning thing here, that you will need at some point using some concepts and tools from probability, logic, and computation. So we are very glad that we can give you some ideas in that respect. But then I have another, you know, aspect of you, but because, well, you are PhD students right now, but you will be citizens all along. And our hope is always to contribute to people being active citizens. And we believe that those topics, the topics we're going to talk about here, are actually very important tools in the toolbox of critical thinking, if you want to use this expression. So yeah, we actually believe that what we do is useful, right? So that's why we're here. Okay, so that's really what I could give you in general for motivation. So if you weren't really sure about why logic at this point, I hope I just gave you some reason to stick to this. Okay. let me just be clear about what we're not going to do. So this prevents useful misunderstandings. We're not going to give you formal introductions to anything. That's not a curricular course. It's just we're going to give you ideas mostly. We're not going to give you self-contained presentation of any topics. So if you at some point develop an interest in one topic or another, you just ask us for more details. Okay, just do that, please, if you find yourself in that position. And unfortunately, given the time constraint and the variety of the audience, of course, we can't really give you tools that you can just pick from this course and use in your research. Okay, so please don't have that expectation. But again, what we hope to do is to get you eventually to have some useful ideas. So we actually try and do this by, again, giving you a feel for the importance of topics and, of course, related as far as possible to your research. I'm going to give you examples of how it works. So that's the spirit of the course. You're not going to see the details, but hopefully you're going to see how it works. Okay. Some hints for further readings, and probably the really most important, the single most important thing, we're giving you someone to ask questions if at any point during your PhD the need arises for that. Okay, so do get in touch. So do get in touch with us, and us actually means the three of us. I didn't say before. I said before I wouldn't introduce ourselves because I'm doing this now. So we are actually in this particular moment a subset of the logic group. So logic group is Marcello D'Agostino, is myself, Heike Hosni, and Giuseppe Primiero, who's not here, so let me not highlight his name. And we have 4 postdocs at the moment: Paolo Baldi, who's here, Fabio, who's here as well, and then we have Esther and Costanza, who will be doing this course next year. So the idea is that we rotate among ourselves this course to give people the widest possible view of the topic. Okay, but we all have something in common. So it's this thing that we call logics for practical reasoning, which really includes the key topics of this course. So we work on what we call realistic models of inference. We really have a common interest in reasoning under uncertainty, and we do like computational intelligence. So, as you see, these are really the topics of our course. It's useful if you find this interesting, that you can keep in touch with us. So we advertise news and all kinds of events and things on our Twitter account. And we do have a web page where our research, teaching material, and everything just gets uploaded. So if you, in the future, this is really about, if you have questions to ask, here we are. Okay, so just please feel free to do this, even if none of us is your official supervisor. That we don't care about this. What we care about is talking to people who have an interest in what we do. Okay, good. So that was really the initial part of motivation, and I felt I should just insist on one specific aspect of what we're going to present, namely the idea that we are giving a sort of AI perspective to the whole idea. And it's really useful to have this. Of course, it's not necessary to give introductory material. It's not necessary to give an AI perspective. But I think it's very useful for those 3 reasons. First, AI really originates within logic. This is something which people may not necessarily be aware of, especially if people approach AI from the machine learning angle. But really, AI starts with logic, within logic, and with logic. So it's useful that you have this idea. AI does incorporate logic, though this is much more recent, if you like, but its probability is a very important part of AI, especially now in the machine learning approach, but also in the in the more, let's say, theoretical approach. You'll see some of these things later on. And of course, AI is computational at heart. So it really is the idea, background story, if you like, to illustrate what we intend to do. And just 3 links, 4 links, maybe to just give you, if you don't have that perception, that AI is everywhere, right? In science, society, medicine really is everywhere. It's going to be increasingly more everywhere. So again, a good awareness of the foundations, I think, is very useful. So this is a 3-4 pages paper by the Royal Society, which does illustrate what the title says: AI Revolution in Science. This is actually I think it's edited by the Alan Turing Institute. But anyway, in combination with the Royal Society. So really, AI revolution in science. So it's big words. And in society, so the OECD has a very interesting policy-making guideline for transitioning to going digital. So that's the name of the program. And 2 more papers, one from Nature and one from The Lancet, for the relevance of AI in medicine. So this is nothing, of this just is necessary for understanding what we're going to do. But again, I think it's useful background. Okay, so I'm just going to finish the introduction. Okay, so that's the plan for today. Let me just say one thing I didn't say in our presentation. So I'm actually doing today just this very broad overview and motivation. Then Paolo and Fabio will just take over and just give you the introduction to the topics that we chose. So I think I'm very actually that I think I am very grateful to both of them to just taking time to do this, and I'm very happy that they did, because as postdocs they're really focused on research, and this is the best perspective for you PhD students to get acquainted with ideas. So just getting ideas from the people who are really developing them. So I think it's a very good match for everyone. So let me just give you some key ideas. First logic, then probability, and finally how this just conflates to the foundations of science and AI. Okay, so logic. What's the role of logic? So gave you this very general motivation, breathing, analogy, and everything. Now let's just focus on, we're doing science here. So what's the role of logic in science? It's a very difficult and, of course, very broad question, but it's very useful to have this picture in mind. The absolutely first role of logic is what people call usually knowledge representation. So you do have an intuitive idea of what knowledge is. For this matter, it's synonymous with information, with knowing things, being informed of things, maybe believing things. Let's just take this very informally and very loosely. You have to represent those things. Okay, so this is the first task at which logic is very useful. It is the first thing for which logic is very useful. And actually, you can ask slightly more precise questions here. So, how do you actually encode? So the keyword here is encode. How do you actually encode logic in an information system? So this is rather broad concept, but an information system is a system. Let's not define what a system is, which processes information, right? So that's an information system. The question is, how do you actually represent the things which are being processed by the system as information or knowledge? Okay, and I'm going to give you some examples of this. Once you've chosen this representation, are all representations which are possible equally good to that purpose? That's a slightly more complicated question, which will be indeed illustrated with examples during the course. So, but it's a very important one. So, there's not a. The idea is what I want you to start. Well, I want you really to start with, on the, on the right foot here, and formalizations are almost never unique. So you have to make choices. When you formalize, you have to make choices, and it's good practice that you know how to actually make those choices. Okay, this is actually true. So this choice of formalization is actually true of all mathematical modeling. Okay, it's very rare that you have a unique mathematical model for the problem of interest. Okay, and of course the question is, okay, this is what I do. This is a way of doing it, but I still haven't answered the question as to why should I do it? Okay, what is there to be gained by representing knowledge logically? And I'll try and give you a hint at a solution to this problem, or an answer to that question. Okay, so first bit is knowledge representation, but then of course, as you probably expect, the really good, well, not necessarily good, but the reputation of logic is really tied to reasoning. So getting knowledge and actually deriving consequences or conclusions, or making inference from that knowledge. So first question is, what is a desirable property? What properties are desirable of good reasoning? And of course, you might think of validity, coherence, though sometimes inconsistency or incoherence is good too. But anyway, these are the kinds of properties that you're interested in. And it's really an analog to, let me just link them. It's an analog to that question. What particular properties of reasoning are context dependent? So this is a very, very important point. Let me just go back to the motivation, the AI motivation. There is in the press, let me put it this way, there is a somehow implicit belief that machine learning will just provide you with tools to address any kind of problems. But we know, and logic is very good at telling this to us, that formalisms, models, mathematical models, have a very, at some point, very important context dependency. So I think this is a very good methodological lesson that you can learn by learning some logic, and the so-called non-classical logics that you will see in this course are really giving you a very good example. So yeah, that's the role of logic. Let me just give you examples now of these things. Okay, so knowledge representation. Here is some knowledge or information. Okay, so I'm giving you, this is information in elementary number theory, arithmetic. Okay, so n is a, let's say, natural number. Okay, let me just add this. Okay, it's a natural number, and I'm giving you some information. If n is a natural number which is greater, which is prime and greater than 2, then n, it is odd. So I just, I'm just struggling because I'm reading this logically, but now my purpose was actually to write it as you would say this, right? If n is a prime greater than 2, then it is odd. Okay, so that's the information, which actually I hope you agree is true. Okay, so first representation. This is the representation of what is called propositional logic. And what you do is you just go in this natural language, English sentence, and you isolate the smallest units which actually makes sense as isolated statements. So the idea is that the smallest unit are statements. Let me just write this. And a statement is very simple to define. Is the if you put it as the simplest form is the kind of content which, if you put as a question, admits only a yes/no answer. Okay, so it's the kind of information which, once you phrase it as a question, the only possible answers are only yes or no. So n is a prime is clearly a statement, right? Because I have a definition of what a prime number is, so I will say yes if n is a prime, and I will say no if n is not a prime. So in logic, what you do is you say, okay, it's really elementary, because I can't really just find more elementary statements in it, right? This is a unit of statements, so I just call this P, okay? Then I actually have some hidden information in here, because in English I'm saying if n is a prime greater than 2, etc. I'm saying if n is a prime and n is greater than 2, right? So n is greater than 2 is another statement which doesn't contain more elementary statements. So the idea is I'm calling this Q. Okay, and implicitly I'm just reading an end here, right? It is odd, of course, if you just take it like this, it's not a statement, but of course you are assuming that you're talking about n. That's the parsing of the English sentence. So this just says n is odd. And again, it's if you ask, is n odd? You will say yes, if n is indeed odd and no otherwise. So it is a statement. It's distinct from the others, so I just give it another name, and this is R. Okay, so let me just try something which will not work, namely changing columns. Yeah, oh, it does work. So I have 3 elementary statements and 2 words which connect those statements, and in fact they're called connectives. So this is AND, right, which in logic you write like this, and then you have an if then, which connects this first bit with the second bit, which is just phrased, captured by this arrow here. Okay, so this is how you read it. If n is a prime number and n is greater than 2, then n is odd. Okay, so you've just 2 is a translation of 1 in what is called propositional logic. Okay, propositional really stands for the fact that you are talking about statements, or as people call them, propositions. Okay, It's useful for later on. A statement or a proposition. Proposition, I suggest you do not use, okay, because it's philosophically very loaded and complicated. So I suggest you avoid this. Of course, if you don't do philosophy, then it's just a word. But if you do philosophy, I recommend you do not use proposition. So a statement is, I told you before, you can think of the essence of it as the kind of information which, if put as a question, will admit only yes and no, of course, or no as answers. But you can actually think of it more interestingly as follows. So the test for something to be a statement is whether you would conceive of betting on it. Okay, so if it makes sense to bet on it, then it is a statement. Okay, I'll go back to this later on. So you can actually bet on the event that n is a prime, and of course you will learn about the outcome of your bet once you know who n is. Okay, and so on. Right, so first, this formalization here is the knowledge representation that you will do in so-called propositional logic. Okay, then you have another one here, which I hope is just as clear as the other one, and is using the notation of set theory, elementary set theory. So, what's the story here? The story is you assume that P is the set of prime numbers. Okay, so you just index this with P. And then G is the set of numbers which are, numbers which are greater than 2. So let me just, for clarity, let me just say this, okay? And so this is the intersection. So those are the prime numbers which are greater than 2, okay? So what this compound statement is saying is the following. If you pick any, let me just change the color, let me just give some kind of yellowish thing to this. So suppose you pick a number which is prime. No, but yellow is not a good choice because you probably can't read anything. So let me just go purple if I can. So suppose you pick this number here, right? What this information is telling you that if you pick a number which is both prime and greater than 2, then you have to pick an odd number, okay? So it's a very different thing, right? Because this and this just do not appear to be at all the same kind of information. So if you suppose you were to train a machine to understand this, what we're going to call a sentence. So a sentence is a combination of elementary statements. If you want to train a machine to understand that, it's a very different business to actually teach the machine this or this. Right? You can see that that's a very different perspective. Of course, the translation given in 3 is much closer to this, right? But this is the pictorial view. Okay, so this is the Venn diagram kind of representation. So this is saying that if you pick any number which is both prime and greater than 2, so if you pick a number in this region, which is shaded here, then you will have picked an odd number. Okay, of course, I've chosen this just because it's absolutely trivial, right? So the point here is not, learning mathematics. The point here is understanding how you can represent this information. Let me just jump to this one. So this one is, okay, let me just follow my order. So this is the so-called first order logic. So let me just write it here, first order, which says the following: for all natural numbers, if for all natural numbers n, if n is prime and n is greater than 2, then n is odd. Okay? There is a very, very big difference between 4 and 2. And the difference is the following. When you translate this sentence 1 into 2, you lose essential information. Okay, the information that you lose is the fact that you all along you are talking about the same number. You're talking about the same object. Once you translated this into P and Q implies R, you just lost all logical connections. And the logical connection is you're talking about the same number, which is exactly what this variable is highlighting in the writing. So this is to say, not all logical representations are the same. So if to your purposes, the fact that you're talking about the same number is essential, then this is no good representation. You have to choose this representation. Okay? The interesting thing is that this continues to be indeed acceptable. And the reason for this is, well, it's kind of technical, is that you actually, to express this in mathematical terms, you need an extension of this logic. So it appears to be exactly the same thing, but it's absolutely not the case. The logic for 3 is actually even more expressive than the logic for 4. Okay, of course, there's no chance I can actually explain this, but it's an interesting feature that at some point you may be reminded of. Okay, so what is 5? What is this beast here? Okay, this is yet again another way of saying exactly the same thing. Okay, so some of you maybe saw these things before, maybe none of you did. This is the one way of representing logical circuits. Okay, so this is the well, if you want to have a very, very loose analogy, this is what an electrical switching circuit would look like. Okay, so this is the NOT gate. So let me just write it here, and this is the OR gate. Okay, so those are the same. So if you read this, this says Q, then, so Q is the input, right? Then you negate Q, so you get not Q, and the output of this gate is the input, one of the inputs to this gate, okay? So let's just go here, you start with P, so Q means this, right? P means still this, right? So you start again with P, you get not here, so not, which means not P. And now you have not P and not Q being the input of the OR gate, okay? So this gets not P or not Q, okay? And this is now the input of another OR gate, which connects this and that. So this is not P or not Q or R, okay? Which happens to be, under certain circumstances, clearly all of those which belong to what we call classical logic is exactly the same information as that. But you're actually representing it with a picture which doesn't have anything to do with that picture, and it's got to talk about electric, if you like, switches. Okay, so this is logic gates. So this is a logic gates kind of representation. Is one of the most important things when it comes to why logic is important, because it really the theory of logic gates is really what allows your computer to actually do logic, right? And that is it really is what connects mathematics and engineering in developing computers. Okay, so apparently a very, very simple thing just can be represented in at least, let me just say, this is not an exhaustive list. This bit of knowledge is just representable in a number of distinct ways. So this is, so sorry, I'm just saying video stopped working. Does it make any sense?
Yeah, you're stuck.
I'm stuck, but do you actually see my slides?
We see your slide, but
yeah, it's okay. I mean, they're way more interesting than me. So.
Yeah.
Okay. Thank you, Bob. Okay, so logic, knowledge representation is really a very important part of logic, especially if your interest is information systems. Okay, if you want systems to reason, the first problem you have to solve is to give those systems a representation of knowledge, a representation of information. And here is just a suggestion that it's not that you can do it, you can do it in a number of distinct ways, which, up to certain conditions, turn out to be equivalent. Okay, so this is a key strength of logical representation, but it's not its biggest strength. Its biggest strength, in my view, is this. So it's the same sentence, so it's the same information, so it's actually two, which is represented in a tree form. And this actually is one way of just showing the immense power of logical languages, because this is called well, there are many names for this, but usually you would call this a parsing tree. This is a terminology which is sometimes used also in linguistics, though maybe with some slightly distinct connotations. But anyway, it's a tree in the mathematical sense, and it's parsing because if you look at the tree, there is a unique way of reading it. You start from left to right, and so you can just, as you would say, mechanically construct the sentence by just parsing the tree. So you start from this corner and you just go up and you say, hey, this is a conjunct, this is another conjunct. So that's a conjunction. And then there is the other conjunct. So this is the conjunction P and Q. And then that really is the antecedent of that implication. So P implies Q, sorry, P and Q implies R. Then actually, this object is defined recursively. So recursion is a keyword in the whole business. So this means that you actually have a precise definition which tells you how to produce all parsing trees starting from a given set of propositional variables. I'm not going to go into any details because some of these things will be covered later on. So this P, Q, and R are called propositional variables, and you have a definition which generates uniquely all these trees. So in particular, that definition will also tell you that this is the way you should group the parentheses, okay? This is absolutely important for so many reasons that I can't really tell you any of them. I'll just tell you one thing, that the parenthesis is really, really important because you're looking at what people usually call syntax here. So the idea of syntax is that this object is distinct from this object, right? So the reason they're distinct is very simple. So suppose you are a machine and all you can do is to just read the characters, okay? So first character, you agree, right? Open parenthesis on both lines, so this is good. Second character, you know, P is distinct from Q, so at the second cell, you just stop and say those two are not the same sentence, okay? So in particular, what you just see is that from the syntactical point of view, P and Q is distinct from Q and P, right? But of course, you have all reasons to believe that as far as information is concerned, in this sense, that really saying the same thing, okay, which is absolutely the case in classical logic. But to actually say this, you have to go one step further, exploit the recursive definition of your sentences, and actually give the logical operators, the connectives, a precise meaning, okay? So let me just continue the example I was just giving you. So I just told you here that P and Q is distinct from Q and P, and the reason for this is the three characters, first character, they disagree, so they're not the same thing, but they are actually equivalent. They mean the same thing. Sorry. Q and P. So what's the meaning? The meaning is the Boolean table. Sometimes people call this truth tables as well. Well, actually, most people. I don't like that expression, but anyway. So what's the meaning of conjunction? Okay, the meaning of conjunction is exactly this. Meaning of conjunction is that when you're asked the question, you say false if both P and Q false. You say false if P is false and Q is true. Similarly, you say false if P is true and Q is false. And you say true, one, if and only if they're both true. So that's the meaning of conjunction. Here, conjunction is just an operation that links, connects, says that P is one conjunct and Q is another one, okay? The table tells you what the actual meaning is, and this meaning is important because it is exactly what allows you to say that P and Q and P are distinct sentences, but they mean the same thing. And that coincidence of meaning depends on the fact that they have the same Boolean table. Okay? So this is the second half of the key thing about elementary logic. The first one is that your language is completely unambiguous. There's no ambiguity. So the point here is that you have no ambiguity. And the reason why you have no ambiguity is that this is unique. Okay? Because if you wanted to draw the parsing tree, of course, I haven't given you the definition, but I hope you can see this. If you want to draw the parsing tree of Q and P implies R, this is not going to be good anymore because you have to start from Q, right? So that would be, so that's another one. That's why I said it's unique, okay? So uniqueness and recursive nature of the thing allows you to actually give meaning to all sentences that you can construct on those propositional variables and these connectives. So this is called negation. I know you probably know all this, but let me be sure. This is called conjunction. This is called disjunction. And this is called implication. So there's no controversy in conjunction. P and Q is true. If you don't leave, they're both true. Well, no controversy on negation as well. If you say that P is false, if you know, for instance, that P is false, so suppose P is today is Friday, right? So today is Friday. Can you bet on it? Yes, it makes sense. Suppose I just woke up and I didn't know what day it was. It would make perfect sense for me to just bet on what day it is. Okay, so it's a good statement. And suppose I know that today is not Friday, because I hope you agree, today we know it's not Friday, then negating to say it is not the case that today is Friday has to be true, right? And similarly, if I negate a true sentence. So there's no negation is absolutely non-controversial. Conjunction to some extent is not controversial. Disjunction tends to be a bit more controversial because it says the definition of the meaning of disjunction is that a disjunction is false in just one case when both disjuncts are false. Okay, so this actually means that a disjunction is evaluated to 1 when both disjuncts are evaluated to 1. This is quite different from what people usually mean by disjunction in natural language, because usually you say, do you want to go skiing or do you want to go swimming? You know, and it's very odd that you understand that you have both options at the same time. Okay, but I suggest this is not the best way of looking at this. And I will illustrate this in the case of the most controversial of all of them, which is implication. And the reason why I chose implication is that implication is the essence of logic. Okay, logic is about implication. Of course, you can complicate very much the story, but if you want to go to the essence of it, logic is all about implication. Okay, so the Boolean table says that an implication is evaluated to 0. Let me just make it more visible. It's evaluated to 0 in just one case. Okay, and that case is the case in which the antecedent is evaluated to 1 and the consequent, as it's called, is evaluated to 0. In all other cases, the implication is true. Okay, this is very, very different from most uses in natural language. So in philosophy, there is actually, it's a very, very active tradition of trying to make sense of this. You know, the fact that people in their linguistic practice they use implication, or as it's called, the conditional, and meanings which are in ways which mean something else. So I want to spend a couple of minutes to show you, to actually suggest that you consider this argument as stating the reasons why this is the way it is. So here is the argument. Just take the sentence you had before. So n is a prime number. If n is greater than 2, then n is odd. That's exactly what we did so far, we did before. Now I'm just giving it the mathematical status of a theorem. Okay, that's a theorem. That's an important thing in mathematics. When you have a theorem, that means that if you agree with the definitions, this has to be true all the time, right? And I hope you share this, right? Any prime number which is greater than 2 is odd. You can prove it, right? It's an obvious definition. Sorry, it's an obvious definition. So, consequence of the definition of an odd number. Okay, so what is this? Why is this related? So I want to justify this table, right? Why is this related? Well, it's obvious why it's related. Let me just make it more obvious. It's an implication. It says if, then, right? So there's something here which is an antecedent, and then there is a consequence. So there is a P. So let me just, n is greater than 2. Sorry, it's a prime greater than 2, right? This thing, let's agree, is just P. Okay? Prime number greater than 2 is P. And n is odd, let's consider it to be Q. This is going against what I said before, because I said before that the representation for that was P and Q implies R, but for my purpose here, it makes no difference. So let's just formalize it in this way. P implies Q. Okay. Now you know that this is a theorem. So I hope you can say it. If you can't, you'll be able to prove it by yourselves later on. It's a theorem. This holds for all natural numbers. This holds for all natural numbers. Okay. So it's true. It's true for all natural numbers. Let's just try and make substitutions of natural numbers to. Sorry, this shouldn't be. That's a feature of the LaTeX thing that I used. It should not be capitalized. So this is n. That's the same n, right? So n. So suppose n equals 8, and let's substitute 8 in this theorem, right? It must be true. The statement, the sentence of the theorem must be true because it's true for all numbers, and 8 is a number, so this must be true. If 8 is a prime greater than 2, then 8 is odd. Okay, this must be true, and the reason why this is true is the truth of this general statement. This is true for all n's. 8 is a number, therefore this must hold. But this actually corresponds, so 8 is not a prime number, of course. Okay, so P is false, right? So if this is P, then P is false because 8 is not a prime number. Similarly, 8 is not odd, so Q is false again. Okay, so here is the situation. We're describing this with V stands for valuation, which is exactly what defines the truth table. So the case n equals 8 is just one instance of V1, is this row of the Borden tables. Antecedent is false, consequent is false. So we're actually plugging 1 in here because we know this is true. This is true, right? And the reason why this is true is not the table, right? We're justifying the table based on this sentence. It's not the other way around, okay? So I should have just filled out the numbers as I went along. So that would have been probably a better way of doing this. So suppose I'm doing this, okay? So this is false antecedent, false consequent. I know that the sentence is true, so false antecedent, false consequent, I just write 1. Okay? So that's one case. Then, oh, that's good. I actually meant to do this because I wanted a fresh page every time. So again, this is n, right? Let's just plug different numbers. Now it's 9. So 9 is a prime, again, sorry, 9 is a prime greater than 2, again is P. 9 is odd, again, now is Q. So is 9 a prime? No, therefore P is false. So we're in one of those two cases. Is 9 odd? Yes. So false antecedent, true consequent. This is the correct description of this situation. What's the value I have to plug in here? Well, I know this is true. The implication is true. And the truth of this depends on the fact that the implication holds for all natural numbers. So, true. Okay? So what you learned in both cases, right? False antecedents give you true implication. Okay? Let's move on. Sorry, it should be 3, right? If n is 3, I get this. 3 is a prime greater than 2. This is P. 3 is odd. This is Q. And now they're both true, because 3 is indeed a prime number. It is indeed greater than 2, so it is one of those two. 3 is odd. Yes, it is odd. So V4 is the correct description of the specific case in which n equals 3. And I know that the implication is true. Why is that? Because it's true for all n, for all natural numbers. 3 is a natural number, therefore the implication is true. So true antecedent, true consequent gives me a true implication. So yeah, plug 1 in here. Okay? So same argument, substitutions just give me reason to fill the Boolean table as I told you before, namely in this way. Okay, so as this one remaining case, so let me just try and hear your voices here. So which substitution do I have to make in order to get, sorry, that's 3. V3. So I have given you an example of V1. V1 is false antecedent and false consequent. So 8 is neither prime nor odd, so it does the job. V2, I just suggested you take 9 because it's not prime, though it's odd. Okay, and then I just gave you 3, which is both prime and odd. So please, anyone tell me what number should I just plug in to account for V3?
A number which is not part of the natural number set, so I don't know, a negative number.
Okay.
I don't know.
Okay, so that is not really allowed
No.
because as I said before, when you do elementary number theory in this way, you actually well, actually you could do that. Okay, so an integer, so a negative number would not really be a problem. Okay. And the reason for this is, so suppose you just give me an integer, just give me a negative number. So I'll show you why it's not a problem. Yeah, just give me your favorite negative number.
-5.
Right. So n equals -5. Okay, so this is really in this case, so right, because it's not greater than 2, so P is false, and it is odd, right? So we covered that already. Okay, so we're V2. We're looking for V3. Okay? Then, of course, you might have a situation in which you're looking for n, and n is not a number. Then would be if you. So this allows me actually to be more specific about what I mean by statements. So suppose I substitute for n, I substitute a vacation to Switzerland. Okay. So, and if I want to just substitute, let a vacation to Switzerland be a prime number, if a vacation to Switzerland is greater than 2, etc., then that just doesn't make sense. So it's not a statement because I just don't have the true, false, yes, no test. Okay, so that's the idea. So I bought you some time to give me another answer now. So yeah, negative numbers just do not really give the answer. So which substitution for n can I make to
an even number?
An even number. Let's try an even number. So that is actually 9 is even. Okay. So it's again 2. Because 9 is, oh, sorry, you said even. Sorry. An even number. Okay, so 8. Yeah, 8. 8 is an even number. Okay, so yeah, it's case 1. Yeah.
So, theorem is true. No substitutions shouldn't be able to find one.
Yes, that's exactly it. So there's no way that you can substitute. You can never find an n which accounts for V3. And the reason for this is that the theorem is true. So it has to be V of whatever has to be 1. And there's no way that you can find that because, that's exactly the case in which an implication is false. And since you can't make that substitution, again, this is justifying the fact that true antecedent and false consequent give you a false implication. This is actually the scenario which in mathematics you refer to as counterexample. Okay, and there is no counterexample to that, and the reason for that is it's true. Okay, so there's no counterexample to the Pythagorean theorem. Okay, if you take a square triangle, you have no choice of A, B, and C. That does not satisfy the equation. Okay, so that's the similar thing. Okay, so good. That was the answer, which showed me that you understand the whole argument. Okay, so the point is, when you look at this, well, let me just go back to the table. When you look at the table, that gives you, it's just one way, it's not the unique way of doing this. If this introduction was given to you by Paolo, Paolo would very probably show you another way of defining connectives because he comes from a slightly different logic tradition compared to mine. But yeah, the beauty of it is it doesn't really matter because eventually it all says the same thing. But this is my favorite thing. So it's really the meaning of logical operators is fixed by mathematical practice. Okay, so when you look at elementary logic, what's indeed it's going to be called classical logic when this is relevant. it is really given to you. The meaning of logical operations is given to you by the idea that you're looking at mathematical arguments. Okay. In fact, the justification for it is along those lines. You can do similar things for disjunction and conjunction and so on. So there is an interesting question, of course, is, okay, what happens when I just want to use logic outside mathematics? Because what I gave you now is a justification for the meaning of logical operations in mathematical reasoning. But if you just want to, you know, try and draw the area of reasoning, maybe mathematical reasoning, if it is that dot in there. So it's a very, very small proportion of all reasoning. Is logic useless to that reasoning? No. Okay, it's very useful, but you have to know how to handle it, so to speak. And that is exactly what we're going to show you in this course. That the elementary logic that you actually learn at school, this is really what you learned in school, is very useful as a starting point for doing logics which are indeed applicable to non-mathematical reasoning, non-mathematical contexts. Okay, so this is really a warning. If you ever come across the expression paradoxes of implication, please be aware of the context of reasoning in which they are formulated. If they are formulated outside mathematical reasoning, then there's no paradox at all, because the definition of implication that I just gave you, the classical logic definition, is justified only in this context. I'm actually giving you a philosophical position by doing this, but I think it's a very robust one. So, and actually, you can convince yourselves about this, you know, just by repeating the arguments with distinct statements. Okay, so are there any questions about this?
Yeah,
Sure.
Is it, can one say that implication is like the only logical operation that can identify, like, that is sensible to the identity of the terms, meaning that the other operations like disjunction, conjunction,
Yeah,
you can evaluate it, and also exclusive disjunction, you can all evaluate it just by knowing like the number of true terms, right? Whether like, for example, conjunction, if there is 2 true propositions, then it's true. So you don't know. You don't know the.
Yeah, I mean, what you're saying probably is this. So if I want to, in general, so suppose I don't really know this, I'm just using A and B to just say maybe it's more complicated stuff. So if I want to evaluate a conjunction, let me just check if I understand what you mean. You know that this is true if and only if, so you have exactly one condition, they're both true, right? And this is, you're saying, not so in implication because you have 3 cases, right? Is that what you're saying? But you can actually write it in a clever way, and you say that V of A implies B equals 0 if and only if you have one condition, which is A equals 1 and B equals 0. So indeed, you can formulate appropriately all the conditions as if and only if statements.
No, but what I'm saying is that if I don't tell you the identity of who is true and who is false, then you don't know whether the implication is true.
But that's true for all cases. So yeah, that allows me to say something. It is actually related, something I didn't say. So the point about this definition is that if you take any sentence, so let me just remove this. So if you take any statement that you can construct in this way. So for instance, suppose it's something complicated like P and Q, or not Q implies P and Q. Suppose it's something like this. Of course, I'm just inventing it, okay? Suppose it's this. The recursive nature of the logical language and this definition guarantee that I actually have an algorithm to compute this value. Sorry, too many things. I have an algorithm to compute this value uniquely. Okay, it's the same uniquely as before. And this is because the truth value of any sentence is a fixed function of the truth value of P and Q. But suppose now that this sentence is containing, so 1, 2, 3, yeah, so it implies R, okay? Now, I don't know anything about R. There's no R in here. So this is not solvable. I cannot say, right? This remains unknown. And that is actually telling you that to know the truth value of a complex sentence, you have to have as input the truth value of its components. Okay? So you can't, in your example, to know the truth value of P implies Q, you have to know P and you have to know Q. Because if you don't know one of them, then your answer is not determined uniquely.
Yeah, but I think I was saying just something simpler, which is in conjunction and disjunction, it's symmetric to changes in the inputs, while the implication.
Oh, sorry. Okay, so yeah, it was simpler, but I hope it was useful what I said. Yeah. Anyway, it's something I wanted to say anyway. Yeah, okay, thank you. Yes, indeed. So if you write, let me just write it here. Q implies P. So that's what you're saying, right? This is going to be 1 here. This is going to be 0 here, 1 here, and 1 there. So if I change the order, as you said, I'm changing the truth value. Yeah. So what you just said is that conjunction and disjunctions are commutative. Yeah. And implication is not. Okay. Yeah. Sorry, I just made it more complicated. But anyway, I wanted to say that. So, yeah, but that's right. Yeah. So that is exactly the case. And indeed, there is more than that. These are dual to one another in a way that maybe Paolo will talk about. So this is to do with, maybe you heard about this, De Morgan. So maybe if Paolo didn't have this in mind, maybe he could just make 1 minute at some point to just address this. Okay, so I don't know why I'm having this thing here. Well, doesn't matter. No. Okay. So I'm actually rather slow, but it doesn't really matter. So having said this, so this is justified about mathematics. So the big challenge is going outside mathematics. So this is really motivating the idea of non-classical logics, which you will see in some examples. Okay, so this is an introduction to that. But actually, what I just said about the truth value of any sentence being computable, is being a fixed function of the truth value of its components, so really the Boolean table is of course, in conjunction with the recursive definition of the language, is really the essence of a very famous quote by Leibniz, who in this sense is to be considered the one of the forerunners of artificial intelligence, because you said, give me a precise enough language, okay? The parsing tree gives us the precise enough condition, and define your terms meaningfully, as we did with Boolean tables. This is really sufficient to solve all disputes among people, okay? So when there is an argument between people, and in this case it says about between philosophers, with my tools, which are really classical logic, if you like, what I told you so far, you can just sit down and compute. So calculamus, right? The idea is the knowledge representation of logic gives you an algorithmic way of really defining the truth value of sentences. And this actually means objective, right? There's no dispute among people. You sit down, you calculate, the solution is unique, and by the fact it is unique, it is objective. Okay, this actually is considered by many the beginning of the idea of AI, though actually there is a neglected forerunner, is actually the person to whom the whole concept of an algorithm is due, and that is Al-Khwarizmi. And if you never heard about him, I really suggest you have a look at the Wikipedia page and the maths history, because he's actually the guy who invented the method that we know as algebra. So his idea was really mathematical reasoning is computation. If you like, Leibniz generalizes this idea by saying all reasoning is computation. And those two ideas, of course, are the conceptual background for the very idea of artificial intelligence. Okay. Indeed, you can see with our tools that you can set up an algorithm to decide the validity of logical arguments, which is what you are interested in when you do elementary logic. Now, deciding is a technical term, if you like. It's just a decision procedure is an algorithm that tells you yes if the argument is valid and no otherwise. Okay. So to do this, you have to know what an argument is. So you can think of an argument as a set of premises on the top of this line, and so this is the set of premises. So that's the kind of all men are mortal and so on, and this is the conclusion. So it's all men are Socrates. Okay, so conclusion. Sorry. Right. So what you want to do is to just define validity. Okay. So validity is defined like this. So an argument, this argument is valid if there is no row in the Boolean table such that those are all true and this is false. Okay. So there's no situation in which all the premises are evaluated to 1, while the conclusion is evaluated to 0. So let's just give an example of this. So just P and Q, so two variables. This is the whole story, the Boolean table. Then Paolo will tell you more details about these things. So don't worry if you just feel that I'm not giving you all the details. This is not the goal here. So you have as premises P implies Q and Q. So those are two sentences. Your conclusion is P. So let me try and see if you can reason intuitively about this. Is this a valid argument?
No.
Why is that?
Because you could have P, like Q being true and P being false, and it's Still true.
So you can have P being. So I'm writing what you're saying. P being
false. No, sorry.
No.
Yeah, you could have.
So the definition is this is valid if you have no situation, and a situation is just one of those things here, in which those two are evaluated to 1, and this is evaluated to 0. Equivalently, if every valuation, so every row of the table, which satisfies, so which sends this whole thing to 1, so both to 1, also sends this to 1. Okay, so it's the same. So,
you can have V2, right?
V2. So V2 would be what?
It would be a it wouldn't obey the scheme.
Yeah, so it's a counterexample.
Yeah.
Right? So V2 just gives you that so according to V2, this is 1, okay? Q is 1, so they're both 1, but P is 0, okay? So this just is the counterexample. And since there exists a counterexample, it's not valid. So what I just did is really, I just applied an algorithm. So the algorithm is this. So you use the table and you just you write down the values. So this is the truth table for the implication, or the Boolean table for implication. This is just a very simple example, so you don't have to write anything. This is this, right? This object here is that. And so you check, right? Every line which gives 1 to both, and you actually have this and this, must also give 1 to P. So this actually does the job, but this doesn't. And that is actually the counterexample. So the definition of validity in this setting actually comes with an algorithm to say yes, no. And actually, this is true for any argument that you write in this logic, which is propositional logic. So any argument whatsoever is going to be solvable in theory with this algorithm. Okay, so have a look at the second example. So let me just do this. So again, P implies, sorry, too much. P implies Q is evaluated here. P is not even evaluated. I'm just writing down the values. So I have to look for a valuation that sends both to 1. So it's actually just have 1. Just 1 satisfies the condition. So, okay. And in that unique valuation that satisfies the premises, Q is evaluated to 1. So yes, this is a valid argument. Okay? So that's the idea. It's a very, very powerful idea. And to some extent is exactly what Leibniz dreamt of. A language and a set of definitions which, no matter who is actually putting forward the argument, just uniquely determines whether the argument is valid or not. Okay, it's a very, very powerful idea. It has lots of limitations, but we're here just to appreciate its relevance. Okay, let me just go quickly through the probability bit, because I kind of assume that in some form or another, what I just said so far was entirely obvious to you. This may not be so obvious. So let me just go quickly here. There are a number of people who thought that probability is really common sense put mathematically. It always makes me laugh because you can actually read these quotes in a number of presentations, and it's true. They actually said, probability is common sense put in mathematical terms. The thing that people rarely observe is that there are three geniuses, right? So the common sense of a genius is not exactly the average common sense. So that's why uncertain reasoning is tricky. Right. So if you're Laplace or Maxwell or Poincaré, maybe, some things are obvious to you, but we're not like them. So we need to just try and understand what the actual reasoning does, what the actual probabilistic reasoning. So I try to start introductions to probability in the most, actually one of the most straightforward and concrete ways. So experimentally, so to speak. So get yourself a die from any game that you have and roll it. Roll it as many times as you want. You will define what people call the sample space. So this is the set of the all and only the outcomes which arise by rolling this die of yours. Okay? You get number 1, 2, 3, 4, and so on. If it's a regular, usual number, you get 6 outcomes. Okay? If you make a very, very big assumption and you assume that the die is fair, which doesn't make any sense unless you know probability, but let's suppose you do know what it means. So the idea of fairness is no side is more probable than any other side. But of course, if you don't know what probability is, right, you can't really decide whether the die is fair, so you assume it. Right? You observe it, you think, oh, it's quite symmetric. It doesn't look fishy, so it's fair. Fair means every side is as probable as any other. So if you make this assumption, it's immediate, or at least I suggest that you convince yourself that this equation holds with no problem. Okay, so the sum of the probability of each side is 1. And the reason for this is if you consider the die to be fair, you would consider each side to have probability 1/6. And the 6 of them, so 1/6 times 6 equals 1. So that's the reason. And of course, you can just consider subsets. So you're just saying, well, I'm rolling, and on the next roll, I maybe get 1 or 2. So the probability of that is the sum of those two probabilities. The reason for this is really the beginning of the whole calculus of probability. You're considering your sample space and you are making a partition of the elementary outcomes. This means that when you roll the die, at least one number comes up, and at most one number comes up, which means exactly one number comes up, and that is giving you very good reasons to assume that this holds. So let me actually give you a reason for that. So the whole business of probability really is measuring things. So suppose I'm just measuring the events in here on the probability scale. So the probability, let me just use colors to see if that works. So the probability that a number comes up, which means the disjunction of all those elementary outcomes, let me just draw it in red, is mapped to 1, okay? When you roll the die, one number comes up. So it's either 1 or 2 or 3, blah, blah, blah. You don't know which is which, but you're sure that one of them comes up, okay? Similarly, it's difficult now to draw the event that nothing of this sort comes up, but if I could draw it, I would map it into 0, okay? Now, suppose I'm just considering this event here. This event is mapped in the roughly 1/3, sorry, 1/3 point here. And the reason for this is that it's the obvious one, is what I said before. Well, it's not obvious at all, but it's familiar. Right? So let me use that. Let me try and change the color. So suppose I'm giving this is 1/6, 1/6, so 3, 1, 2, 3, 4, 5, 6. Okay, so suppose that's the thing. And each one of them gets mapped into, so individually, they're all mapped into 1/6, okay? And so on. So this is really probability, is taking sets of outcomes and grouping them in such a way as to just really measure them on the 0-1 ruler. Of course, this is the real unit interval. So this is the 0-1. It's all the real numbers between 0 and 1. Okay. It's actually methodologically important that you observe that it's not my way, or it's not the most usual way. It was actually the only way the whole calculus could start, and this has to do with the nature of these objects. So, as I said, every time you roll a die, you will get a result. Okay, and you get exactly one. And those two are essential properties. There's a question. Oh, okay. So those two are exactly the required properties to get the mathematics of probability started. So if you have an interest in this, just have a look at this. This is so wonderful. It's rather old, but it's still one of the best introductions to the early history of probability. And really, it really stresses, it shows you why there is no coincidence in the fact that the beginning of probability was gambling games. Okay, the technical word for this is that when you roll a die, you have full knowledge of the stochastic device that produces your random variables. So that's the reason. Okay. But let's just make it a bit more interesting with 2 dice. Okay, this is just to show you that until quite recently, people were very confused about these things. So Leibniz makes this famous mistake of considering getting 11 and 12 equally probable when you throw 2 dice. Okay, his reasoning is that, well, I can obtain both 11 and 12 in one way. So 11 is uniquely written like this, and 12 is uniquely written like that. Okay, so it's a 5 and a 6 is 2 6s, therefore just one way of producing each, therefore the same probability. Okay, it's an intuitive reasoning which is wrong, and the reason why this is wrong is just the following. I'm giving you the whole picture. So to do this, you have to distinguish the 2 dice in some way. So let's consider one black and one white. Okay, so those are the individual sample spaces, what can happen individually, and what you see in the inner part of the table is what happens when you roll both. So in this case, you got 2 1s, okay? in this case, you get A2 and A1, which is not the same as this one, right? The sum is the same, so 3 is 2 and 1, but what happens is the fact that in this case, your 2 was black, in that case, your 2 was white, so distinct outcomes. So you see now where the mistake comes in. So Leibniz just correctly identified 6 and 6 as the unique way of getting 12, but there are two distinct ways of getting 11. So probability of getting 11 is strictly greater than the probability of getting 12. Okay, so you can do this now because your mathematics is good enough to know everything you need to know about Cartesian products. So this is what the thing is. Leibniz didn't actually have that. But yeah, more importantly, this is a very schematic, but I think extremely useful example of the fact that probability is very tricky unless you have perfect knowledge of the mechanism which generates the uncertainty which you are quantifying with the probability measure. So I said many difficult words, I know, but this is what the example is saying. I know everything about what can happen here, which is exactly why I can tell with great confidence that this, right, 11 is more probable than 12. Okay, so you can see it, it's there, right? Not so if you don't know exactly the mathematical properties of the mechanism which generates the uncertainty. Now, let me just make a big leap here. Think about a medical diagnosis, right? Let me challenge you into producing the elementary outcomes of a probabilistic evaluation in any diagnostic problem. Okay, it's a hopeless task, right? It doesn't have to do with the fact that maybe it's a continuous set, right? Assume it's continuous, it's fine. Problem is you don't know what's relevant, right? You don't know what's independent. You can't have a complete picture of what generates your the condition that you're trying to diagnose. Okay, so the mathematics of probability is extremely reliable when your problem comes in a form which you or somebody who does this, you know, as their day job, can actually say, look, I know the stochastic mechanism. But if your problem is such that you can't really make that claim, then probability is extremely fragile in its applications. Okay, this is a very important methodological point. Of course, we can't really go into this direction, but this is the message. Probability is an extremely useful fundamental tool, but it cannot be applied everywhere with the same confidence. Okay, this is the take-home message of that. When you actually can apply probability reliably, then you get beautiful stuff. Okay, those are the laws of chance, if you like, or the properties of random variables, distributions, stochastic processes, all the kind of things that just are taken for granted when you do, let's say, medical statistics. When you define a clinical trial, you are using a couple of, well, let's say 100 years of beautiful work in the laws of chance, okay? And let me just summarize the idea here. So it's in the dice thing. You throw in, so I'm just rewriting this in another form. You have sets, right, which are indexed by the sum of the points which you obtain, right? So set indexed by 2 is the set of outcomes which give you a sum of 2. So just one case, okay? So mathematically, you say that the measure of that set is 1, okay? Well, actually, it's a bit misleading now to say measure 1. Well, actually, is the frequency in this situation. So this be careful, okay? I just realized now this ambiguity. Of course, this ambiguity doesn't mean much to you now, but be careful. Okay. So the frequency, so the number of times, okay, in which the number of distinct ways in which you can get the sum to is 1. You have just one way of doing it, and it's both dice come up 1. The sum of 3 you can get in 2 distinct ways. So that's the frequency of 2. Sorry, frequency of 3 is 2. Then sum 4 you can get in 3 distinct ways. Okay, so one white die comes up 1, and black comes up 3, 2 and 2, 3 and 1. Please note those are not the same outcome. Okay, so 3 distinct ways. 5 you get in 4 distinct ways. 6 you get in 5 distinct ways. 7 you get in 6. 8 you get in 5 ways, and so on. Okay, this is together with the assumption that each outcome is as likely as any other outcome, is sufficient to determine, in fact, uniquely the probability of that event. So the probability of you getting a sum with 2 dice is 1 over 36. Now, 36 is the number of elements in this inner part of the table. Okay, you can get it in exactly one way, so it's 1 over 36 possibilities. I assume this is all absolutely familiar to you, right? Of course, you just move along here. But the actual thing that I want to show you is just this. Just have a look at this picture here, and actually maybe I can help you by doing this. Now, this should remind you of something, right? Does it? Have you ever seen a picture like this? Maybe I can help you.
The binomial distribution.
Yeah, well, not exact. Well, yeah, let's say the normal. Yeah. Okay. It's okay. Let's say the normal distribution, the bell curve, the only probable, probably the only picture in probability that everyone at some point in their lives saw. Okay, so this is the one of the keys, not the necessarily the, but one of the key laws of chance. If you have a way of producing uncertainty which has certain features, which we now call Gaussian, after Gauss, of course, you can actually make a number of inferences. You can deduce many things, okay? And you see it's completely symmetric. It's a beautifully symmetric object, right? So it's difficult now to do this, but yes, very difficult for some cognitive reason. Okay, so that's the average, the mean value. And actually, you see, the mean value is what you can expect to get, right? If you replicate this experiment a very, very large number of times, right? So if you throw those dice, very many times, then this is the most likely outcome, okay? Which is actually also known as the expectation of your random variable. And as a very last observation on this, next time you come across a die, please have a look at the distribution of the points on the surface, right? If you look at the dice, what you realize is that the sum of so suppose this is how it lands, suppose this is 1, okay? If you just look at the parallel face is going to be 6, right? And if you're looking at 3, the opposite face is going to be 4. So it's the points on your dice are just represented in such a way that opposite faces sum up to 7. You might think, okay, this is, now we know the mathematics of this, so people know the expectation. The beautiful thing is that this configuration of regular dice has been like that since the ancient Egyptians. So it's about 6,000 years to some accounts. So yeah, that's the laws of chance. That's how beautiful it is. This is beautiful, and it always. It is useful only when your uncertainty fits this picture. Okay, when it doesn't, you have to do some work. And this work actually started with one of the people who started the mathematics of logic, namely George Boole, to whom we owe Boolean tables, though he didn't actually use them, but he actually figured out what they would be. And in the introduction to the fundamental book in logic, known as the Laws of Thought, he actually adds a very important subtitle, which people very often neglect, which is the following, on which are found the mathematical theories of logic and probabilities. So, to Boole, logic and probability are just two chapters of the same thing. Okay, so here is a couple of quotes in which you can see that he actually states this explicitly. So that's actually the opening statement. But what I want to say is the next bit. What I want to emphasize is the next bit. So he says, given the probabilities separately attaching to the premises of any train of argument, it is always possible by his method to determine the consequent probability of the truth of a conclusion legitimately drawn from such premises. So here is the extension to probabilities of Leibniz's idea of calculus. Okay, and this is how things go wrong. It's a very beautiful idea. It really matches this, okay? So this is, I think, 1854. The analytical theory by Laplace was really out for 4 decades. So the whole behavior of Gaussian variables was very well understood, but that's not what he really refers to, okay? His idea is, I can just as I showed you, you can compute the truth value of a sentence uniquely, or the validity of an argument uniquely by using Boolean tables. Boole just said, well, I can do that with probabilities. Trouble is, his book is full of mistakes, and that actually is not possible. But the idea actually was very important in relating logic and probability. Okay, so this is a picture by Bruno De Finetti, who played a very, very important role in developing the theory of probability in the century. He draws this beautiful picture. So he starts with an event, which is a statement. It could be P in our language so far. And he says, logically, you might have that V of P equals 0 or V of P equals 1. Okay? It's just as we did so far. That is logically. Then you may or may not know that value. Okay? So suppose you know that value and you know that the value is 0, then your uncertainty is really not meaningful. You know that the probability of that has to be 0. So suppose we bet, suppose P is today is Friday, okay? It is not the case that today is Friday, and we actually know it is not Friday. So suppose now somebody asks you to bet on today being Friday. Okay, how much would you pay for that? Well, how much would you pay for a bet which will give you 1 if today is Friday and 0 otherwise? Well, if you had some time, which you don't have now, you will figure out that the only answer is 0. If you know that something is false, then you have to give it probability 0. Similarly, if P is Monday, then you know it's Monday, you know it's Monday, therefore the probability that today is Monday has got to be 1, right? But interesting case arises when you don't know. Suppose this is again Monday, but you don't know, it's true, but you don't know it, okay? You're uncertain about it. Then the whole thing about probability is that you can map your uncertainty into the real unit interval. In this case, you're looking at the percentages, but of course, it's the same representation, right? So this is a beautiful picture that tells you there is a strong connection between logic and probability. In this sense, you see that probability builds on logic. Logic constrains probability when you know the values, right? Okay, and it does also constrain your values when you don't know it, but it doesn't constrain the values uniquely as Bull hoped for. This opens to a number of very important points, which I don't have time to go through. So let me just skip all of them and just give you the actual punchline. Probability is not compositional in the way classical, in fact, many logics are, in the sense that if you know the probability of 2 events, this doesn't give you sufficient information in general to compute the probability, say, of their conjunction. Okay. And this actually is not to some accounts, well, actually to many accounts, the fact that probability is not composition, so that the probability of a compound sentence or event is not uniquely determined, is actually a good feature, right? So let me just skip this. Because I just don't have time. We started late and I just spent more time on the introduction. So let me just give you, I ask you to believe me here. It's not possible to compute uniquely and objectively probabilities, okay? Which poses a very important problem in the applications of probabilistic reasoning in sophisticated systems, such as machine learning applications and the general AI applications. So I'm sorry I just couldn't develop this. If you want to know more, just please let me know. Well, actually, you can let me know and maybe ask either Paolo or Fabio if you're interested in this to develop some details. Okay, so let me skip the whole thing here. And let me just say one more thing. I'm sorry, I'm just using more time than I planned to, but you, Fabio, can probably just redistribute some material later on. So let me just use this picture I gave you before to give you an intuition for what is really this, a key contribution to science and AI. And that is the notion of conditional probability. Suppose you're in this situation, it's the two dice situation, and you have two events. So event A is you're getting 3 with the black die, and event 4 is the sum of the points that you get is 9. Okay, the question is, what is the probability of A given B? Okay, so that's the idea of conditional probability. I'm skipping all the details because you'll see some of this later on. So how do you do this? Well, first of all, you have to remind yourself of the space of possible outcomes of this experiment, which is just the table you saw before. Okay. Now you have to represent your knowledge, and your knowledge is the sum of the points is 9. Okay, somebody comes in and says B. Okay, that's the idea of conditional probability. And the way you represent this is just you delete everything which is inconsistent with the sum of the points is 9. So what you're left with is only the 4 possible cases in which the sum of the 2 dice is 9. Okay? You can convince yourselves that there's just those 4 cases. Your question is, what is the probability of A given B? Namely, what is the probability of black? Let me not do this 3, right? So what is the probability of this, okay, given that sum is 9? Well, you have just 4 cases in which the sum is 9. Okay, therefore, the probability of A given B, it's got to be just 1/4, because of the 4 surviving cases, only 1 is compatible with A. So what's the probability of black 3 given that the sum is 9? There is just 1 case, right? So probability 1/4, right? So probability of, well, let me not just repeat this. Okay, so this, why this is key, and why is this so important? Because you can see how you, according to how you interpret this, so this is called the, well, conditions, and this is called the conditioning event, and this is the conditional probability. So the conditioning event plays the role of knowledge that you learn, right? So somebody says B, okay, by the act of saying B, everything which is not B gets deleted, okay? And then you just, the new, so kind of the new omega. So omega 1 now is just 4 elements, and only 1 has the property that you want. Okay, so you learned. You just change your initial probability. And what I mean by this is, suppose you're not conditioning. So what's the probability of A? Probability of A is this thing. So is you got 2, 3, 4, 5, 6. So is 1/6. Okay. Once you learn that the sum of the points is 9, the probability moves from 1/6 to 1/4, and that is the consequence of you learning B. So this concept is really probably the single most important concept in probability as far as machine learning is concerned. So it's important that you see the idea, and then maybe you'll have some detail later on. But this is really what connects logic, probability, and the current applications of machine learning. Indeed, you can. This is the usual notation for conditional probability, which is just a more abstract way of writing what I said before. So the probability of A given B is the ratio, is the fraction of the probability of B and A to the probability of B, which, if you take the measuring approach that I suggested before, is really the ratio of two areas. So is the ratio of degree, so the probability of A given B is this thing here, and the probability of B is this area, the pink area. So is the ratio of the green to the pink area. Okay, so suppose this actually corresponds to those numbers. You assume that the probability of the square is 1, so you get probability of A is relatively small, probability of B is 1/4, right? Probability of A and B is again rather small. It's the green area. But if you condition on B, you see that it goes even further down, because you're just having a fraction with the denominator bigger than the numerator, so the value diminishes. As your colleague rightly pointed out before, implication is not symmetric, and so is the conditioning operator. In fact, if you just do the reverse fraction, then you see that the value increases from 0.2, you get 0, sorry, from 0.02, you get 0.26. Okay, and it's this, the fact that conditional probability is not symmetric, is the key thing in distinguishing correlations from causation, which plays a very, very important methodological role. So again, there's no aim here in being, as I said before, as I promised, in being self-contained. I just want to give you a picture, but please stick to this picture when you think of conditional probability, because this is really what you are doing. And conditional probability is the key notion, is actually the only notion involved in Bayes' theorem. So I just gave myself space here. Bayes' theorem is just the obvious consequence of the fact that conjunction is commutative. So A and B given B, right? So you can actually obtain this. Let me actually leave this to you as an exercise. This is what you have. What you want to get to is this: P of A given B equals probability of B given A times probability of A over the probability of B, right? So exercise, so really exercise. I actually gave out the answer. But anyway, yeah, so this is the definition, that's the thing we saw. And this is Bayes' theorem, which forms the conceptual background for Bayesian statistics, which is one of the cornerstones of machine learning. Okay, so it's an immediate consequence of this picture, really, and it plays an extremely important role. So it's useful that you know that it just arises like this. It's just a very simple. It's really the key to Bayes' theorem is this analysis, which is justified by this. So this argument that I gave you before justifies exactly this equation, and the actual proof rests on the observation that your colleague just gave before, namely that the commutativity of conjunction. So This is true under all valuations. Okay, so sorry about just just taking this long time, but we started late, and I just was really concerned about the clarity of the motivation for this. So that's the reason I insisted quite a lot on the first bit. The point is really to just hopefully give you a good reason to learn more about these things. And of course, you're welcome to just get in touch with me and of course Paolo and Fabio with any questions that you might have or interest that you might have in the neighboring areas. So are there any burning questions on this? Maybe before we take a 5 minutes break, everyone. Are there curiosities or anything about this? Please be very open. No, we're really in an informal setting. So. No? Okay, so I suggest we take a maybe 5 minutes break. And so we reconvene at 5:10. Okay?
Yeah, good for me.
Yeah, sorry, can I ask you how long, because on the syllabus it wasn't really mentioned, like the time schedule.
Yeah.
So, and on